Turning the music on is a six-sided hexagon, and they all get in line and do a dance called the nine-a-gun. Oh, sorry, I have geometry on the mind. Alright, so 10-4, normal curves for FST, changing gears in my own head. Yes, normal curves. We were doing lots of binomial distributions lately, and we were... Yeah, I always start with that page, and then I forget that I need to show you this page. Look at that, there's a new record, nine questions in the do now. You notice from last class I'm going to start doing this. I'm going to start not having a second page of do now questions. I'm not going to have a do now that goes back to the homework that was already due today. Like today when we were talking about 10-4 in class, I'm not going to have a do now about 10-2 and 10-3. I'm just going to really go over the homework 10-2 and 10-3 really well. I think the sort of triple coverage was wasting a lot of time, and we didn't get to enough good time in class of you going over homework questions and the new homework questions with me sort of around to help. So this is going to be it for the do nows from now on. It's just going to be over the videos. So I want to make people more accountable for the videos also. I think it's going to help do that. Anyway, here's your 9 questions. Okay, after saying I was going to shorten up the time on do nows, I'm giving you a 9-question do now. These are all really short though. Like they're one number answers, so they should go fast, except for maybe the last one. Okay, there we go. Yeah, we've been doing binomial distributions a lot recently. Binomial distributions were like, you know, that thing with the six questions, and originally there was these bars that kind of look like this, the 6 questions and the five possibilities. And I said if you added more bars, the bars would start to get really close together, and the curve would start to get smoother, and you know, the stair steps wouldn't be as chunky. Well, if you went to actually, you know, n here was 6, and then I think the next example n was 100, and it looked a lot like this, and the maximum starts to come down. You know, the most popular answer here, the most popular score on the 6-question test was like 40%. The most popular here, I think I guessed, was like 5%. Then the question is, what if we actually went to thinking about this over an infinite number of cases? We're going to let the limit of this be infinity. What if I had as many cases as I could possibly imagine, and this gets ultimately completely smooth? What does it look like, and how do I get an equation for that curve, and how does it behave, and what's the area under it have to be, and all that kind of stuff? Well, someone discovered this, and you're not going to believe how much it has to do with other areas of math. This seems pretty crazy, but really this comes from nature in a lot of ways, because it comes from you know, the regular old we're expanding this kind of thing. These two probabilities add to 1. We're graphing the probabilities for the different members of this expansion, and there's, you know, Pascal's triangle in that, and that comes from, you know, natural places. What I'm trying to get at is this normal distribution curve you're about to see is not invented by somebody. So a lot of people say, oh yeah, the normal curve, that was invented by somebody who was just trying to make standardized testing and trying to get people filed into categories and say that no one could get an A, or you had as many A's on a test as F's on a test. No, this is simply pure mathematics. It comes from expanding a binomial where you know that you have a certain % chance of failure and success, and you're letting the limit of the exponent of that thing go to infinity. Well, unlimited exponents, that should remind you of something. That should remind you of things like e. I believe e was the limit of this thing as n went to infinity. I don't know, something like that. As n goes to infinity, that thing kind of starts to turn into e. Well, yes, e is involved here again. E, using the base of natural logarithms, they have constructed a curve. I say they have constructed a curve. They discovered a curve. I just said this is a discovery, it's an invention. There's a curve that will model this perfectly. And they go into in the section, they go into a huge discussion about, in the book, about how this curve that you want to model all normal distributions looks kind of like this. You know, this shape. You know, but okay, it's supposed to be symmetrical. It starts from this parent function. They take this parent function, and then they have to sort of manipulate it so that it behaves and goes right down to the actual normal distribution for the normal distribution curve. Okay, if you take this thing and actually divide that exponent by 2, so this is e to the negative x squared over 2 power, which seems kind of wacky, you get this nicely shaped curve. But it's a little bit too high. It's a little bit too... oh wait, they don't divide that by 2 at the beginning. I think this is actually... It's a little more parenty, like it's a little more generic. It's a little easier to digest at first when they talk about it this way. This is actually at the top of page 650. And top of page 650, they're talking about this one. And they're talking about how this has a nice maximum at 1. This thing is going to have an asymptote of 0 in both directions. It's not actually going to hit the axis. You can think about that as x goes to infinity. This exponent's going to get negative huge, but it's not going to get to, sorry, we're going to e to some huge power. But remember that exponent's negative. And they don't say it this way in the book, but remember negative exponent is like saying 1 over e to the x squared. And e to the x squared, that as x gets huge, this gets huge. 1 over huge starts to look like 0. And if e is negative, sorry, if x is negative, squaring x is going to give you the exact same values as it did when x was positive. So we have this line of symmetry here. We're going to have an even function. Meaning if I put in a positive number for x or a negative number for x, I'm going to get the same value for the height here, which is kind of what you want on this pass-fail thing. Like we've found this kind of symmetry in a lot of these binomial expansions, like Pascal's triangle, for one thing. The number of ways, if you're going to get on that 6-question test, if you're going to get 2 right, the number of ways to select which 2 you're going to get right is the same as getting 2 wrong. So you get this nice kind of symmetry too. All right, but this graph doesn't behave quite well enough because we don't want the area under the graph to be this big, and we don't want some of the other stuff to happen. Oh, another thing that happens with this one that's a little bit weird, they have this thing called an inflection point. This point here is called the inflection point, and it's a critical point, especially if especially when you start studying this in calculus and trying to compute the area underneath it, and deciding how things are changing, all that kind of stuff. There's 2 points of inflection on this thing, and I don't know if you've ever heard about points of inflection before. There's one there and there's one there. The points of inflection happen when you've got a curve that, maybe I should start with a different type of curve. First of all, down here we say the curve is, it's kind of going that way. It's kind of like if it were raining, it would be catching the rain, or actually be sliding up that way. That's not a good way to describe it. It's what we would call open up. The tangent lines in this part of the curve, from negative infinity up to this point, this is where things change. The tangent lines would be underneath the curve, for one thing. There's a point of tangency. If you can imagine that line that's tangent, it would go underneath it, everywhere over here. Whereas over in here, the tangent line would hop to the other side. This part, you would say, is from here to here is what we would call open down. Does that make sense? Open, down. I'm asking questions. I'm asking questions of a viewer. Does that make sense? That I'm asking questions. I'm asking myself questions in front of viewers who aren't even here. Okay. Too much geometry. And over here it would be open up again. I don't know why I'm drawing these above and below on the little blue waves. Point of inflection is kind of where, like, imagine if you were driving along this, and kind of here you're turning very slowly, but you're kind of making if we're going sort of an easterly direction here, you're kind of curving the car slightly to the left, and at this point you're going straight, and at this point you change to turning left. Sorry, what did I say? We're turning left here. At this point you're going straight, and after that you're turning right. The tangent line is kind of your direction, I guess, that the car is actually heading at the time, the velocity, if you think in physics. And at that point the velocity changes from a lefterly turn to a righterly turn, and we're turning right here this whole time, and then we start turning left again. So yeah, these, I don't know how the best way is going to speak to most of you about what exactly inflection points are, but that's what it means. So sometimes in math they talk about the part where it changes from open up to open down. Sometimes they say that about the tangent line hopping to the other side. A lot of times I actually talk about where the second derivative is 0, if you've heard that before, which I think might come up in physics with velocity and acceleration. Anyway, inflection points are important. We kind of want to keep track of those. All right, well, this is just the parent function. This isn't the right sort of size of what we want it for normal distributions. It has to be manipulated so that a couple of key features come into play in terms of where this maximum is and where these inflection points are, and what the area is underneath it and stuff. Oh, one cool thing about this one, the area under here, oh, I gotta change color. It's just too cool. It deserves its own color. The area under this curve, you're not going to believe this. It's all starting to come together now. And by that I mean infinite area. The area of all this stuff under the curve, all the way out here getting skinnier and skinnier and smashed down to infinitely short. The area under all of this, now how do they figure this out? They do not expect you to figure it out. They expect you just to hear about this and not believe it because it's just so unbelievably cool. But the area under this curve happens to be the square root of pi. pause for gasp. Can you believe that? I don't know. It's not really important if you believe that or not. And they really don't tell you in the FST book how they get this. It involves a lot of calculus that I didn't study until second semester college. But they're just kind of saying, hey, guess what? This has other connections in math and in nature, and you better believe it's not just something somebody made up. All right, on to 10 minutes. I'm rambling. But really, you notice there's not a lot of calculations in this section. It's just a lot of what is the normal curve. They save the calculations for later. So the first thing they do with that normal curve is they divide it by 2, so it gets a little bit spread out a little more. Ooh, that's a little too slopey, but it's still, basically this shape. Yes, you've heard the word bell before. It kind of looks like a bell. They divide it by 2 in the exponent, and then they also put this constant out front, 1 over the square root of 2 pi. So now we've got this being sort of a constant multiplier, and we're taking the exponent and cutting it in half. If you do that, then you finally get everything you want to happen as a statistician. You get the inflection points to happen at nice places. You get the maximum to happen actually at a nice place. And those key features are described in notes. Let's go through those now. I'm not going to be able to write them as well as I've already typed them. Here's the parent function has these facts about inflection points and stuff. I think I've already said that. But domain and range is listed there. It's kind of nice. You can pause this now and read that if you want. Here's the stuff about the final one, the standard normal curve, which is incredibly important and valuable for finding statistics all over the book and all over real life and all over your adult, highly functional member of society future. All right. Yeah, the range goes from the maximum here is 1 over the square root of 2 pi. The maximum in the center of that graph, the center is where x is 0, and the maximum is actually right here is about it's this number because it's when x is 0, so this is actually the value of y, which is about 0.39%. Actually closer to 40%, but that's the height right there. Okay, it's an even function. They call it the z-axis now. Now, why on earth they do this? This is an invention of human beings. Why all of a sudden we call this the z-axis? It's not the z-axis because we're all of a sudden hopping into 3D and this is coming at your face. No, this is still y. They call this z because pretty soon they're going to chop this up into numbers of standard deviations, and that's traditionally called a z-score. So we have 1 standard deviation, 2 standard deviations, and we're going to talk about the area under this a lot. And that's always referred to as a z-score. I think x is just supposed to be something like the actual person in the actual spot, and then z is more like a bucket of people, like a histogram. I don't know who came up with the z-axis thing. It's not horrible. It's just, you've seen z-scores when you're talking about SAT results and that kind of thing. It's just now we call it y and z all of a sudden. I don't know why they could almost put a z in here. That's another feature you need to worry about. So z is just a new name for x. Inflection points are now at 1 and -1. That's kind of a big deal. This is now 1. I said 1. This is 1, and this is -1, where the turning happens. The turn right to turn left change. And the total area under the curve now is 1. So that makes it a good probability distribution now, because you don't want this area to be anything other than 1, because remember this is supposed to represent all probabilities. So that was a lot of the trouble that they went to in this whole manipulation of the thing. You know that the area under here now is 1. Okay, so again, there's not a lot of calculation yet in this section. It's just sort of getting familiar with the normal curve and its properties and where it turns and what things are called and how it came to be. Really what it's good for is, again, it's for when you've got an infinite number of cases. This is what the distribution should start to look like. So when you have a really high number of trials, like you have, instead of taking a multiple choice test with 100 items on it, you could be talking about the entire population of the world and how tall they are or something like that. And you have these averages and you have how it should work out. Or actually something more binomial, like the average lifespan of a certain type of plant, and the binomial thing is kind of about life and death, and how many trials is how long it lives until it dies. And then you're going to start to see curves like this because we have such a huge number of trials in that amount of data. So when the data starts to get huge and you have a binomial distribution, it starts to look like this. Okay, that's hopefully enough description. The homework is not too threatening. I've looked at it all, and I will see you in class.